In this short video, we're going to take a look at a problem that caught my attention on the internet. There is a number of YouTube channels where problems are posed for people to solve. And this was a problem that caught my attention. You know how YouTube is. If you look up a topic, they begin to send you videos that relate to that topic. They target you for those types of videos from then on. Well, I've looked up a couple of math problems just from interest's sake, and so I get these videos. Now, this is one that caught my eye, and along with it, the problem was posed as a problem that has gone viral in China. Now, some of these problems that you'll see on the internet and YouTube are tricky. They often look like simple problems, but there's usually some trick to it that, cleverness, some deep insight that you'll have to have in order to be able to solve it. This one looked pretty straightforward to me, and given the fact that we had done a series of videos on integration, I thought this would be a perfect opportunity to show the power of calculus. Now, this problem can be done geometrically using trigonometric identities and relationships, knowing the area of a circle, for example, is pi r squared and so on. But I didn't necessarily like the solution, the way they went about parsing the problem. And in this case, you do have to parse this problem. Now, look at how this problem is presented. We have the shaded area down at the bottom on the left-hand corner. We have the circle inscribed inside a square, and we have a diagonal section that's cut from the radius r over here, which happens to be 4. Oh, gee, this is weird. I'm getting the size is really kind of strange. Well, anyway. All right. So we have the radius is 4 because of the sides that are given here. We have 4 there, 8. The diameter is 8. And so we have this diagonal, and this diagonal parses the problem up in such a way that it divides the corner area that's outside of the circle within the square, and it bisects it, not evenly, but it does bisect that area, that corner area right over here. And the area that's shaded is the part that the problem tasks you to try to solve. What is the area of that part? And, at first it doesn't look like it could be too terribly onerous. But it's not necessarily a straightforward problem, and the lengths to which the guy went to solve the problem without using calculus was inordinate, and so I found that the calculus approach was the more elegant, not only the more elegant, but the more accurate way, and also probably the easiest way to approach the problem. But again, this is a good example of how the problem is presented and how one should be open to looking at how do I set up this problem so that it's easiest to solve. So I flipped the problem around and then chose the origin to be the center of the circle. And I thought that would be good because it encompasses the entire problem to the first quadrant of the Cartesian coordinates. And in this case, I went against my rule of using polar coordinates when you see circles, generally the rule, but in this case I stayed with rectangular coordinates. Also, the simplest way, I thought, of solving for the problem was not to directly solve for the area of the shaded area directly, which I could have done this area right here, but I would have to break up the interval because finding the limits of integration would be difficult. So I chose the area to be the section identified by the differential area dx dy to integrate because I didn't need to parse it up. All I needed to do was define my limits of integration. And in that case, we're integrating from the surface of the circle to the line in the y direction, and in the x direction from the point of intersection between the line and the circle, and the radius r equals 4. That's the extent to which we integrate in the x direction. So actually, I need to be a little bit more careful here because when I solved this, I didn't get the problem exactly right. So I need to be a little bit more precise in my see, I can set up the problem, but I can't do the addition. So anyway, the unshaded part of that corner area is what I decided to calculate, and then take the difference between the square, the area of the square and circle, and subtract that from the area that I estimate, that we calculate, and that would be the area of the shaded corner, shaded piece. So setting up the limits is now what we've reduced the problem to. So what do we have? Again, we're given that the radius is 4. We have the extent of the line where it's choosing the origin being at the center. So 0, 0 is right there at the origin. So this is minus 4. X is minus 4 right there. And x is 4 is on the positive side. And what I did was I used my knowledge of linear algebra to obtain the equation of a line, of this particular line, in relationship to the origin. And that happens to be in the little box down here on the left. I did the math. You can take a look through the math I did it step by step and found the intercept and the slope, and I wrote out the equation down in the box on the left-hand side of the screen here, the bottom left. Now, on the other side, we have the equation of the circle, which is x squared plus y squared is r squared, and r is 4. So technically, we have y equals the square root of r squared minus x squared, and technically that would be 16. So I didn't put it in here, but that's exactly what it is. And what we do to find the intercept or intersection of the line with the circle, we make y of the circle equal to the y of the line, the same point. And so we have y equals r squared minus x squared equal to x divided by 2 plus 2. And that's what we have on this line right there. And what we do, we end up with a quadratic equation down here doing the algebra, and we solve using the quadratic formula for the x-intercept. And I wasn't careful. I couldn't do my addition properly, and so that should be 2.4, and this is wrong also. So I have to be pretty careful here. I wasn't careful enough, so sorry about that. I apologize, and we'll just erase all non-essential lines, and this is 24. So 32 minus 8 is 24. It's 2.4. So that's the x. That's the x coordinate where the line intersects with the circle. So that's actually the limit in the when we want to integrate. That is this. 2.4 is the smaller part of the limits of integration, and x equals 4 is the outer edge of the limit. And so up here in the middle of this diagram here that I have the area dA equals dy dx, and I'm integrating in the y direction from square root of r squared minus x squared, that's the surface of the circle, to the line x over 2 plus 2. So that's my y integration. My limits of integration in the x direction are 2.4 to 4, and the problem solved. In essence, I mean, we've done the hard part. We've chosen we simplified the problem. We used the principles of finding the simplest way of approaching the problem. I flipped the circle up on its so that the shaded area wasn't in the bottom. It was up in the top quadrant of an xy coordinate that I chose to have an origin at the center of the circle. And I mean, I could choose an origin anywhere, but it's not going to simplify the problem. I got to choose an origin that makes the problem the simplest to solve. And then I decided to integrate that area below the line outside of the circle, inscribed within the square, that unshaded area, and then subtract it from known areas so I can get that area by difference of the shaded area. So that was my strategy, and that's what this integration indicates the thought process that I went through. So in the y direction, I'm integrating from the circle, r squared minus x squared, square root, to the line, the upper limit of integration, x over 2 plus 2. And then in the x direction, I'm integrating between x equals 2.4 to 4. I keep hitting the wrong buttons. And so I have my integral. Now, it's a double integral. Double integrals indicate areas. They're so much simpler than trying to figure out a single integral, because you're thinking about the problem. What are my limits in the y direction? What are my limits in the x direction? How do I set up this problem? What symmetries help me simplify the problem the best? And so I've done all that, and now I have this integration. All I have to do now is solve it. And that's what I do for the remainder of this problem. Each step, each line, is a step that I use to integrate the principles of integration, the laws of integration, or rules for integration, given the limits. Now, my first line here was integrating in the y direction, which puts the equations x divided by 2 plus 2 minus the square root of 16 minus x squared into the integrand of a single integral in the x direction with the limits between 2.4 and 4. And so now I have my integrand that I need to solve. Well, the front end of this integral is simple. It's basically a polynomial, x over 2 plus 2, and that's a simple integral to execute, and it results in x squared over 4 plus 2x, with the limits 2.4 to 4. So I leave that alone for a while. That's a very direct and easy integral to solve, so I just kind of leave it alone. Now I'm faced with the task of what to do with the square root. Well, I have to use a trigonometric substitution, which I did up here. Now I chose x equals 4 sine theta, leaving dx being 4 cosine theta d theta. And all I have to do now is I plug that into the equation, and I end up with an integral that is the square of the cosine. Well, from there I use trigonometric identities to convert or transform the integrand into something smaller than a second order trigonometric function. Whenever you can reduce a trig function or its order of magnitude, it's always best. It tends to simplify the integrations. Also noticing that the argument of the cosine function 2 theta is not problematic, but it just is another dimension that adds to the dimensions of this problem. So I make a u substitution for 2 theta. And with that, I end up with a very simple integral for the first part of this integrand, which just leaves me with theta there, 8 theta, minus the integral of cosine of u du over 2. Now, on this slide, this sheet, I just replicated what we had on the previous sheet, and I do the integration, which of the cosine of u, which is the sine of u, and u is 2 theta, so I have to put that into the argument of sine theta. Well, we don't know what 2 theta is, so we use a trigonometric identity that sine of 2 theta or 2x or anything is equal to 2 sine theta cos theta, and we use that as a representation for sine of 2 theta, and then we go back to our original definitions. We said that x equal 4 sine theta, and we go back to our right triangle, and we devise the sine of theta and the cosine of theta in terms of x, and we come out with a full function here. X squared over 4 plus 2x minus 8 arc sine of x over 4 minus x over 2 times the square root of 16 minus x squared. And now all of these can be evaluated between the x limits 4 and 2.4. And now it's just down to plain old addition. We've gone from calculus to algebra to now simply addition, which can be problematic if you're not careful. And when I do the math, I end up with that corner area, the unshaded piece, has an area of 2.1816, whatever square units we're using. We got to remember that we're dealing with square somethings. Inches, feet, acres, whatever dimension we're using. The last piece is, now that we have this area here, what was that, 2.1856, we take the area of the square minus, what we do is we get the area of the corner, which is what we've done up here, which is the area of the square minus the area of the circle. And then we got the area of the corner. And now the area of the corner minus the area we just calculated using calculus leaves us with the area of the shaded area, of the shaded spot, this part right there. And we end up with 1.2484 square units. So actually, it's a very long decimal. It goes on and on. I don't know if it's completely irrational where it's non-repeating, never-ending decimals. I don't know. I didn't carry it out that far. I only carried it out to the point where I was confident that I had the same answer as the individual who did it using plain trigonometry. So, again, the key to solving this problem is how you set it up, where you choose your origin. What are your limits of integration? You got to think through the problem. How do you set up this problem? That's the real hard part. And once you establish your limits of integration with respect to your chosen origin, then the rest of it comes down to integration. Now, again, that's not trivial, because there are some integrals that are very difficult to solve, or frankly just not solvable. Then you're stuck. Then you have to use numerical techniques. But often you're able to solve the integral. And in this case, you could solve the integral. It wasn't that terrible. We used a trigonometric substitution, and we found, using some identities, the ability to solve that integral. But setting up the problem is like 90% of the problem, and that's really the point I'm trying to get at. But with that said, this is the solution, and this is the area of the shaded spot. That's our answer, and we're happy that we have whatever square units it's in. And it's exactly the answer that was given in the problem. Well, not exactly. He had 1.25 something, and he used an approximation. My solution gave an exact solution. I just didn't carry it out to its entirety with the decimal points. So I guess in a sense it's an approximation. But I think my approximation is certainly more close to the absolute value of the area of that shaded corner than using the method that was given in the video that I saw. And again, I didn't look at the answer until after I solved this problem, and I think that's the way you should look at these problems. And I only looked at the answer in order to confirm my work, and it certainly did. So anyway, this was a fun problem. It says it went viral in Japan, or not Japan, but in China. I'm sure it's viral. If it's viral in China, it probably is viral in Japan. I doubt very seriously that you are going to find too many Americans that go bonkers over stuff like this. But you find that rare individual that really enjoys, problem solving of this nature. It's a shame to say that this is a difference between our two cultures, but it is, and unfortunately, having this knowledge gives them a technical advantage because, again, in technology, mathematics is it. Mathematics is the whole business, the whole ball of wax. So, anyway, this is Math Man wishing you all the best.